Hello everyone and welcome to the video on the fundamental theorem of calculus. This is section 4 of chapter 4. Our objectives in this video. Number 1, evaluate a definite integral using the fundamental theorem of calculus. This is what's going to make our lives a little bit easier in terms of working with definite integrals. Number 2, understand and use the mean value theorem for integrals. Number 3, find the average value of a function over a closed interval. Number 4, understand and use the second fundamental theorem of calculus. And number 5, understand and use the net change theorem. Let's get right to it. The fundamental theorem of calculus. If a function f is continuous on a closed interval from a to b, and capital F is an antiderivative of f, of little f, on the interval from a to b, then the definite integral from a to b of f of x dx is going to be capital F of b minus capital F of a. In other words, if I go through on this particular problem here, I have the integral from 0 to 2 of x squared dx. Now you might remember this because I think we did this one either in class or in the last video. I can't remember which. But we came up with an answer on this one. So let's see if we get the same result. What I'm going to do is I go through and I just have to take the antiderivative of x squared. Well, I know the antiderivative of x squared is going to be 1/3 x cubed. And I'm going to go and evaluate this from 0 to 2. Notice I don't put the plus c. I don't need the plus c there because it would end up, if I put a constant, what's going to end up happening up here, if you notice, here I am subtracting f of b minus f of a. When I put a constant on here, it's going to be subtracted in the second part. So I don't even have to worry about that. So in this case, it's going to come out to be 1/3 times 2 to the third minus 0 to the third, which in this case comes out to be 2 to the third is 8, so I get 8/3. And that was the answer that we came up with in class on the problem when we did this one using the summation formula. So in this case, that area the area between x squared and the x-axis from x going from 0 to 2 is 8/3. Let's take a look at a couple more examples here. What I'd like you to do initially is I want you to pause the video and I want you to find the antiderivative, an antiderivative for the square root of x and the antiderivative of cosine x. So pause the video right now and find those antiderivatives. Once you do, then we'll come back and we'll finish up on this problem, on both these problems. Welcome back. In this case, one of the things that's going to help you out when working on these problems is recognizing that this is as in exponent notation would be x to the 1/2 power. And so when I go through and when I'm going to go and take the antiderivative of this, I know I'm going to add 1 to the 1/2, which will give me 3/2. So the antiderivative of x to the 1/2 power is going to be 2/3 times x to the 3/2, and I'm going to evaluate this from 1 to 4. So when I put that actually evaluate, that's going to be 2/3 times 4 to the 3/2 power minus 1 to the 3/2 power. Well, 4 to the 3/2, when you do that, that is going to, the denominator there represent, we're taking a square root. Numerator tells me we're going to cube it. So in this case, this is going to be, when I do this, it's going to give me, this will be equal to 2/3 times 8 minus 1, where the final answer will be 14/3. What I'd like you to do right now, let's do this. You went through and found the antiderivative of cosine. Well, you found that antiderivative. When you did that one, you should have found that to be sine. So this is going to be sine of x going from 0 to pi/4. Now what I'd like you to do, pause the video, and I want the exact answer to this definite integral. So pause the video, calculate the exact answer of this, and then when you come back, we'll check to see what you did. Welcome back. In this case, when I set up, I found my antiderivative of sine of x, and I'm going to evaluate it from 0 to pi over 4. So I take sine of pi over 4 minus the sine of 0. And sine of pi over 4 is square root 2 over 2. Sine of 0 is 0. So my final answer, the exact answer here, is square root 2 over 2. So the value of the definite integral from 0 to pi over 4 of cosine x dx is square root 2 over 2. The next thing we want to take a look at is what's called the mean value theorem for integrals. And what happens, this is very similar to the mean value theorem that we had dealt with before, in that it is an existence theorem. It tells you something exists. It doesn't tell you where it's at, but it tells you it does exist. So in this case, we're going to say if f is continuous on the closed interval from a to b, then there exists a number c in a and b such that the integral from a to b of f of x dx is going to be equal to f of c times b minus a. In other words, if you look at this, that's going to look very similar to what we did with a Riemann sum. And what we're saying here is that we can come up with a single rectangle. The base of that rectangle is going to be b minus a. The height of that rectangle is going to be f of whatever c is. And when I do that, it is going to be, the result is going to be the exact value of that area. Now that should make sense that that's possible because we know that we have a lower sum where the curve is over all the rectangle and an upper sum where the curve is inside all the rectangles. Well, if there is an upper sum and a lower sum, there's got to be one way that I can go through and get the correct answer exactly. And that's what we're saying here. So one of the things they're going to ask you to do is they're going to ask you to find c. So we're going to let f of x, in this case, equal the square root of x, which again is x to the 1/2 power, and we're going to look over the interval from 4 to 9. So now setting up the definite integral, I have the integral from 4 to 9 of x to the 1/2 power dx equals 2/3 times x to the 3/2, going from 9 to 4 to 9. And so when I plug that into the fundamental theorem, evaluating it, I get 2/3 times 9 to the 3/2 minus 4 to the 3/2. Which 9 to the 3/2 is 27, 4 to the 3/2, as we talked about a little bit ago, was 8. So I get 2/3 times 27 minus 8, which will come out to be 19. So 2/3 times 19 gives me 38 over 3. So now they want me to find the value of c that is going to make this true. So in this case, and remember, c is going into f of x. Well, since f of x is the square root of x, I'm plugging c into it. I'm going to get square root of c times 9 minus 4, which is my b minus a, and that's going to equal this definite integral, which is 38 over 3. Well, 9 minus 4 is 5, so I get 5 times the square root of 3 equals 38 over 3. When I go through and multiply both sides by 1/5 or divide by 5, however you want to look at it, I get that the square root of c is 38 over 15. Squaring both sides, I get 1,444 over 225, or when I put that in my calculator, it comes out to be about equal to 6.418. So the value of c that will satisfy the mean value theorem for integrals in this case is about 6.418. Now the really cool thing about this is that the value f of c guaranteed by the mean value theorem for integrals is actually called the average value of f on the interval from a to b. So what I have to calculate that average value of a function, it's just going to be 1 over b minus a, which is times the integral from a to b of f of x dx. Or you could also look at that as being equal to the integral from a to b of f of x dx, the whole thing over b minus a. Both of those are used for the average value, and it's however you can approach it either way. You should recognize that both will give you the exact same answer though. The other thing that you have now, since we have the idea of a definite integral and we have the fundamental theorem of calculus, we can also use a definite integral now to define a function. Right now, everything we've seen was where the definite integral ends up being a numerical value. We took the integral from a to b of f of x dx, and we would get an area, or we would get some numerical value, either positive or negative or 0. What we can also do is we can use the definite integral as a function of x, where I'm going to let capital F of x equal the integral from a to x of f of t dt. Now what happens here is that means that I can plug different values of x, different numbers in for x, and I can then therefore have a function that I'm working with. So different values of x are going to give me a different definite integral. And so one of the things that we look at with this and we'll use is the idea that this f of x in this case is what's called an accumulation function. Think of it as accumulating area. By changing the x, I'm going to change the amount of area that I'm including in that calculation. Let's look at an example in this one. In this case, I have this graph here, which is f of t. And I'm going to define g of x as the integral from 0 to x of f of t dt. So to start out with, we're going to calculate g of 0, g of 2, g of 4, and g of 6. Well, in this case, g of 0 is the integral from 0 to 0 of f of t dt. And we have a property of definite integrals that told us that when these limits of integration were the same, that was just going to be 0. So in this case, g of 0 is 0. The next one I have is g of 2. That's going to be then the integral from 0 to 2 of f of t dt. Well, when I look at that graphically, we know we're looking at the area, and because we're looking at an area that is below the x-axis, we know that this thing should come out to be negative. And so I know, and I can work with that because I've got if I look at this, from 0 to 2, I'm going to be dealing with a triangle. And I know the base of that triangle, or the area of a triangle, is 1/2 the base times the height. The base is going to be 2 from 0 to 2. The height, if you will, is the function's value, which we'll use as -4. So when I multiply that out, I get -4. So the value of the integral, definite integral, g of 2, is going to be -4. Let's look at g of 4. G of 4 also, when I go from, it's going to be the integral from 0 to 4 of f of t dt. And again, when I go from 0 to 4, I'm looking at a triangle. So I know it's going to be 1/2 the base times the height, which in this case my base is 4, times the height, which again we'll use the function value, and the function's value there is -4. And so when I do that, I'll get 1/2 times 4 times -4 is going to come out to be -8. So g of 4 in this case is equal to -8. Let's look at g of 6. G of 6 is going to be the integral from 0 to 6 of f of t dt. Well, if I look at that, I have the integral. I know this is going to equal, by some of our properties, it's going to equal the integral from 0 to 4 of f of t dt plus the integral from 4 to 6 of f of t dt. Well, I already know what the integral from 0 to 4 is. That's equal to -8. Now I have to look at what's happening from 4 to 6. And from 4 to 6, I do have a trapezoid. And I know the area of a trapezoid is 1/2 the height times the sum of the two bases. Well, in this case, with the trapezoid I have, my height is going to be 4. So it's going to be plus 1/2 times my height, which is 4, times the sum of the two bases. Well, my two bases are the parallel sides of the trapezoid, and that is going to be the base that runs along the x-axis is going to be 2. The base that is up at the high point is 1, so it's going to be 2 plus 1. And so what I get is -8 plus 1/2 times 4 times 3, which is going to be 6, which equals -2. So g of 6 comes out to be -2. Now, because we can now define a function as a definite integral, we also get into the whole idea of what's called the second fundamental theorem of calculus. Because we got a function that's continuous, and we know it does have a derivative because we're integrating something. So what we want to do is we're going to say if f is continuous on an open interval I containing a, then for every x in the interval, the derivative with respect to x of the integral from a to x of f of t dt is equal to f of x. Take a look at that. we're going to integrate this with respect to t, use the fundamental theorem to evaluate it, and then take the derivative. And what this does, both fundamental theorems, but this one really just screams at you, is it ties the two operations of calculus together, the derivative and the integral. For example, we're going to take the derivative with respect to x of the integral from 2 to x of t cubed minus 4t plus 1 dt. And what the second fundamental theorem of calculus says is that what's going to happen is when I integrate that, then take the derivative, all that's going to change is the variable. I'm going to get x cubed minus 4x plus 1. Now, let's take a look at the fundamental theorem where we also have the chain rule, because this is where things get a little bit trickier with this fundamental theorem and how we define it. We're going to define f of x this time as the integral from 0 to x cubed of the square root of t squared plus 1 dt. Okay? So I know f prime of x is going to be the derivative with respect to x of the integral from 0 to x cubed of t squared, the square root of t squared plus 1 dt. Now what I'm going to do on this one is, first thing, I'm going to let u equal x cubed. So when I do that, I get f prime of x equals the derivative with respect to x of the integral from 0 to u of the square root of t squared plus 1 dt. Now the other thing I have with this, by the chain rule, we know one of the things we have with the chain rule is that f prime of x, which is df dx, is equal to the derivative of f with respect to u times the derivative of u with respect to x. So in this case, when I take the derivative of this part right up here with respect to u, that is really getting into just the basic fundamental theorem, second fundamental theorem of calculus without having to worry too much about it. And I'm going to get that this thing, that derivative, the derivative of f with respect to u, is going to come out to be the square root of u squared plus 1. Now du dx is the derivative of x cubed with respect to x, and I know that derivative of x cubed is going to come out to be where I'm going to multiply that by 3x squared. So to finish this one up, to get f prime of x, I know f prime of x, I'm going to replace u with x cubed, so that's going to be the square root of x to the 6th plus 1 times 3x squared. That would be f prime of x on that problem. So notice what's happening. When I'm working with something here, this is going to go in for t, but I have to remember to multiply by the derivative of that x cubed as well to get the final answer. The last thing we're going to look at is what's called the net change theorem. And really, and this is going to look pretty familiar to you. The net change of f on the interval from a to b is the definite integral from a to b of f prime of x dx, which is going to be capital F of b minus f of a. Now notice here, we use capital F prime of x. Well, that we know is also, we can think of that as little f of x. And really, so this is really nothing more than the idea of that fundamental theorem of calculus. But one of the things you have to realize, it's called the net change theorem, and the reason for that is it tells you how much change has occurred. It doesn't tell you like what the end result is. Let's take a look at an example here. I have a tank is being filled at a rate of 180 plus 3t liters per minute. If a tank initially has 150 liters, how much is in the tank after 20 minutes? Well, I know the net change in this case is going to be the definite integral from 0 to 20 of my rate that I'm given, which in this case is 180 plus 3t dt. And when I go and do that definite integral, I get 180t plus 3 over 2t squared. And I'm evaluating it from 0 to 20. And when I plug everything in, I get 4,200 liters. So I've had a net change. During those 20 minutes, I've added 4,200 liters to the tank. Now, one of the things that always happens on the AP exam, they're going to give you something where they tell you what happens initially. And they're going to ask you to go and tell them what the result is after that 20 minutes. Well, the total amount that's in the tank then is the 4,200 that we've added in 20 minutes, plus what we started out, which was 150 liters. So our total amount in that tank after that time is 4,350 liters. Very often, one of the mistakes a lot of students make when they take the AP exam is they forget to add that initial amount into the problem to get your final answer. This now concludes my video on the fundamental theorem of calculus. We'll do a couple more examples in class, talk about a couple things there, but most of the time in class should be spent just working through finding the definite integrals and using some of these theorems. So I hope you are having a good weekend, and we'll see you in the next class.